Yeah, hello everyone. I'm Alex. So how are you today? My topic today is homotopy equivalence. So I'm not going to talk about the definition, formal definition of this mathematical term, but I'm going to demonstrate what a homotopy equivalence is like using various examples. I hope that will be interesting. So let's get to our first example. So I wrote two English letters here. One is D and one is O. Can you tell me about the geometric difference and similarity between these two letters? So who can tell me?
They're
The
all
geometric.
circle-ish.
What?
They're all circle-ish.
Yes, they are all circle-ish. And what about the difference?
One's more circular than the other.
One is more circular and the other is have a straight edge. So we say that these two letters, from a mathematical perspective, they are homotopy equivalent. So homotopy equivalent means that these two are something similar in shape. So actually, homotopy, these first four letters is from a Greek word that means same or similar. And the other four letters, something like means a place in Greek words. So the whole thing means something like the similar or same place. But what you might understand that the place is not like, so what we are talking about the shape, but you mean the similar shape is registered for another word. So what we see in common between these two letters is some like circle-ish. So can we transform one to the other? Of course, it's very easy. Like, you see, there is a straight edge. If you push it, like, push it, and then make it round, so a D becomes an O, right? So, and you can do it backward. So homotopy equivalence is about something you can transform the shape continuously, like making a pottery from a mud, or something like blow up a balloon. So you keep blowing and it getting bigger and bigger. The shape changes. It continuously changes. So we say that these two are homotopy equivalents. They are homotopy equivalent. So let's take another example. So I wrote another two letters. This is one is C, and the another is still O. So you can guess, are they still homotopy equivalent? Like making transformations. You might guess that they are no longer homotopy equivalent because you see this is open.
Yeah.
No matter how you pull it, how you stretch it, and as long as you do not stick these two together, it becomes equivalent. So we say that these two are not homotopy equivalent. Actually, when you do transformations like this one, there are some rules you must follow, like this one. You cannot join something together, you cannot stick it together, and you cannot cut something off. And you cannot also make holes in something. Like if I put it like a metaphor, you blow up a balloon, as you're blowing it up and up, it gets bigger and bigger, and always keep homotopy equivalent. But then if I find from nowhere, get a needle, and just probe it, what you get? It exploded, and it's no longer homotopy equivalent to the original one, right? So here comes another maybe more difficult example. This is an letter A. Another one is also O. So are these two homotopy equivalent?
No.
Your guess is not? Like make the transform. You can contract it, you can expand it, you can inflate it. How about guess? No? That's right. So from A, like the most difference is like this straight line, right? So you can first move it as lower and lower, like blowing it, and contract those two long lines, make it shorter, and blow this up. Like using a mud, you can blow it. I'm not cutting off any lines. I'm not making any holes. So an A becomes this, like this, blows it up, becomes an O. And you can also do it back. Like you are playing with some mud, you can make edges, as long as you don't cut them off. So this is a more difficult example of multiple equivalent. And as you can see, I'll show you another more difficult example, but it's very interesting. I'm not good at drawing. This is a circle. Let's say this is a circle, and this is the center of the circle. And we say that a line connecting 2 points on the circle passing through the center, this is called a diameter, right? So these 2 points, we call these antipodes, meaning 2 points at the opposite side of a diameter. So there was a circle, there were so many points. Imagine that what will happen if you stick these 2 points together. So you can imagine you stick it together, but not only these 2 points. Every point on the two opposite ends of a diameter. We say that if you stick all the antipodes together, what will a circle become?
Board.
Can you imagine that?
Board.
Remember, this is like a 2-dimensional thing, so it cannot become a 3-dimensional thing. Try to
More
imagine.
smaller circle.
Excuse me, 1 minute left.
Okay. So this is an elastic, right? So this is a circle. It always not the same size. Okay, let's try to stick all those antipodes together. These are 2 antipodes, right? Stick it. It becomes like an 8, but not quite, right? So remember, there was an antipode like on this point, and the other point is like at this side, right? It's something like opposite. Can you see that?
Yeah.
Opposite side. When you stick these 2 sides together, this and these 2 points are antipodes. We want to stick them together, but first let's twist it 108 degrees. So it's become really like an 8 with this single crossing, and these 2 becomes
Excuse
antipodes.
me, time's out.